Hello and welcome to our second lecture. This week we're going to finish chapter 1, we'll talk about classification, and then we'll start talking about first order equations. First of all, classification. If we have a differential equation which only includes ordinary derivatives, then it's called an ordinary differential equation. And on these slides, I'm going to be abbreviating ordinary differential equation by ODE a lot. For example, two of the equations that we looked at last week, the falling object equation and the mice and owls equation, are ODEs. If a differential equation includes partial derivatives, then it's called a partial differential equation, or PDE. This course is about ODEs. Now, usually, and including last week, we would have one variable that we wanted to find, so one differential equation would be enough. But that's not always true. If we have two or more unknown functions that we want to find, then we would need a system of differential equations. For example, the predator-prey equations are, or is, a system of differential equations. There's two variables here, two functions that we want to find, x and y, and both of these functions occur in both equations. We can't just solve one equation first and then move on to the next one. We would need to solve them together. In the final chapter of this course, we'll be looking at systems of differential equations. And when we get to that point, we're going to need to use our linear algebra. Another thing to talk about is the order of a differential equation. This is just the order of the highest derivative in the equation. So, for example, the falling object and the mice and owls equations are first order ODEs. This equation, d squared y dt squared plus dy dt plus y is equal to 0. We have two derivatives. Second term has one derivative, and the final term has 0 derivatives. Out of the numbers 2, 1, and 0, what number is the biggest? 2. So this is a second order ODE. Y triple prime plus 2e to the power of t, y double prime plus y prime is equal to t to the power of 4. What is the biggest derivative of y here? It's a triple derivative. So this is a third order ODE. Another term which is important to us is linearity. A differential equation is called linear if it's a linear function, if capital F is a linear function of y and the derivatives of y. Now, the key point to note here is we don't care about the independent variable t. We're only looking at y and derivatives of y. A linear equation looks something like this. We can have a function of t, any function of t, doesn't matter, we don't care about t, so you can have any function of t here that you wanted, but then there will just be a y on its own. And then plus any function of t, and then just a y term on its own, and so on. Another way to think about this is, let's cross off all the functions of t. We don't need to worry about these, so just pretend these are not there. Cross off all of these functions of t. We're going to forget about these. We're also going to cross off all of the derivatives of y. We're not worried about the derivatives of y at the moment. If we have a linear equation, we would be left with y plus y plus y plus y plus y plus y is equal to 0. In this case, the equation is called linear. For example, the two equations we looked at last week, falling object equation and the mice and owls equations, are linear differential equations. An ODE which is not linear is called nonlinear. For example, y triple prime plus 2e to the power t, y double prime plus y prime is equal to t to the power 4 is non-linear because it has a y multiplied by y prime term in it. Let me do my trick from before. Let's cross off all of the functions of t because we don't need to worry about those. Let's cross off all of the derivatives. Then what are we left with? Then we're left with y plus y squared is equal to 0. I don't have y plus y plus y is equal to 0 because I have this extra squared term. Anything that's more complicated than just y on its own means that it's non-linear. Now, some questions for you, just to see if you're paying attention. What is the order of this equation? First order, second order, fifth order, sixth order, or 99th order. Please click one of these options. The correct answer is that this is a fifth order equation. And this equation is a linear equation. If we ignore all of the functions of, in this case, x, oh, there's a mistake here. This should be x, this should be x, or all of the x's should be t's. If we ignore all of those and we ignore all the derivatives, we have y plus y plus y minus y minus y is equal to 0. So this is a linear equation. Let's do another one. The second equation here is a third order equation, but is this linear or nonlinear? if we forget all of the derivatives, forget all of the functions of x, then this would just be y plus cos y is equal to 0. That's not just y plus y is equal to 0. It's more complicated. So this is a non-linear equation. Another question for you. d cubed y dx cubed plus cos x dy dx is equal to sine x. Is this linear or non-linear? This equation is a third-order linear ordinary differential equation. Y double prime minus y squared is equal to x squared. Linear or non-linear? The answer is this is a second order non-linear equation. It's non-linear because of the y squared term. And the final one, e to the power x, 7 derivatives of y minus x cubed, 99 derivatives of y plus 2x to the power x, y triple prime, minus x squared, e to the power sine x is equal to 2021. Is this linear or non-linear? We can cross off all of the functions of x. We don't need these. Cross off all of the derivatives of y. And then we would be left with y minus y plus y is equal to 0. So this equation is linear. This is a 99th order linear ODE. And that's classification finished. Now we're going to move on to talking about first order differential equations. So in this chapter, we're going to be looking at equations of the form dy dt is equal to some function of t and y. And the first type of first order equations that we're going to look at are linear equations. As I said in the previous section, I'm repeating it here. If the function small f depends linearly on y, and I remind you, we don't care about t, we're only looking at y, then we have a first order linear ODE. Now, last week we looked at some linear ODEs of the form dy dt is equal to minus ay plus b, where a and b were constants. This week, we're going to generalize this to looking at dy dt plus p of ty is equal to g of t, where now p of t and g of t are going to be functions of t. Let me repeat or revise how we solved the equation from last week. We're going through it very, very quickly. We started with dy dt equal to minus ay plus b, and we rearranged this so that all of the y terms are on the left and all of the t terms are on the right. If we can separate the variables like this, then we're allowed to integrate both sides. After we integrate both sides and then rearrange, we end up with the solution y is equal to b over a plus some constant c e to the power minus at. So, for example, dy dt plus 2y is equal to 3 would have solution y is equal to 3 over 2 plus c e to the power minus 2t. Unfortunately, we can't use this same method to solve the equations with functions p of t and g of t. So we're going to need a different method. And the method we use is the one from Leibniz. The idea is this. First step is to find a special function mu of t, which is called an integrating factor. We're going to multiply our ordinary differential equation by mu of t, and then we're going to integrate. So, for example, use an integrating factor to solve dy dt plus 2y is equal to 3. We know how to solve this equation from last week. We already know the answer, but now I want to solve it using the new method. We need an integrating factor mu t. We don't know it yet, so let's just keep it as mu t. Let's multiply the differential equation by mu t. So then we get mu t dy dt plus 2 mu t y is equal to 3 mu t. Everything is multiplied by mu t. And let's look at the left side of this equation. Mu t dy dt plus 2 mu t y. I want to find the special function mu t so that this left-hand side is integrable. Now notice that the left-hand side looks a little bit like this. The derivative of mu t multiplied by y by the product rule is mu t dy dt plus d mu dt multiplied by y. And that's almost what we have. There's a mu t dy dt, that's the same. And then the first equation has a 2 mu t, and this bottom one has d mu dt. We want them to be the same. So we want to choose the function mu t such that d mu dt is the same as 2 mu. We know how to solve this. We can use the method from last week. So very, very quickly, rearrange to separate the variables, move all of the mu terms to the left and all of the t terms to the right. Integrate it, rearrange, and we find that mu t is some constant c e to the power 2t. Now, we don't need to find every single mu t. We just need one mu t which works. That means we could choose any value of c that we wanted as long as c is not 0. So we could choose c as 99 if we wanted. We could choose c as 14,102,021, today's date, or If, like me, you like easy functions, we could choose c equal to 1. So the integrating factor that I want to use is mu t equal to e to the power 2t. So we take our differential equation that we started with and we multiply every term by e to the power 2t. And because we've chosen our integrating factor carefully, using the product rule, the left side is just the same as the derivative of e to the power 2ty. And now this is an easy equation. This is an equation which is going to be easy to integrate. Integrate the left side, integral of the derivative, they just disappear. The left side is just e to the power 2ty. And on the right side, we just get the integral of 3e to the power 2t. All that's left is to divide by e to the power 2t, and we get the answer. And if you check back, this is exactly the same answer that I got using the previous method. So to recap, to solve dy dt plus 2y is equal to 3, we use the integrating factor e to the power 2t. Next example, use an integrating factor to solve dy dt plus ay is equal to b. We could repeat everything I just did, repeat the whole previous method, and we would find that the integrating factor that we want is e to the power at. I'll leave that for you to check. What we're doing is we're looking at the constant here. And this will tell us, this is the shortcut, this will tell us what integrating factor to use. Let's make this a little bit more difficult. Now let's suppose instead of equal to b here, we have equal to g of t. The integrating factor that we want to use doesn't depend on gt, it only depends on the coefficient of y. The integrating factor only depends on the number a here. So again, we're going to be using the integrating factor e to the power at. So take the equation, multiply everything by e to the power at. Here we are. We use the product rule on the left side, and our differential equation simplifies to derivative of e to the power aty is equal to e to the power at gt. Integrate both sides. I'm worried that it's going to get a little bit complicated, so I'm using a different variable inside the integral, a different dummy variable here while I'm calculating the integral, and then after that is done, I'm going to replace it with t. So that's just why there's an s there. Divide both sides by e to the power at, and we have a general formula for the solution to an equation of this form. Let's make it a little bit more difficult still. No, first let's do an example. Solve dy dt plus a half y is equal to 2 plus t with the initial condition y of 0 is equal to 2. First, we're going to solve the differential equation, and then we're going to use the initial condition to find the constant. Straight away, we can say that the integrating factor that we want is e to the power t over 2. I'll go through this very, very quickly. You can read this later. Multiply everything by e to the power t over 2. Use the product rule. Integrate. There's an integration by parts here, but not difficult. Divide by e to the power t over 2, and we get the answer. This is the solution to the differential equation. the final step is to find the constant c, which satisfies the initial condition. So I start with y of 0 is equal to 2, and I find that I must have c equal to 2. So the answer to this problem, the solution to the initial value problem, is y is equal to 2t plus 2e to the power minus t over 2. Okay, nothing new there. Solve dy dt minus 2y is equal to 4 minus t. I'm not going to do this one, I leave this for you to check. Check that if you use the integrating factor e to the power minus 2t, because there's a minus 2 just here, then go through the previous method, multiply by the integrating factor, use the product rule, integrate, etc. You can check that the solution is minus 7 over 4 plus t over 2 plus c e to the power 2t. Now let's make this more difficult. Now let's suppose that instead of a number in front of the y, let's suppose that we have a function p of t. We need the integrating factor. And I should give you a warning. The integrating factor is not e to the power pt. Don't fall into that mistake. So how can we find it? We can do what we did before. At the moment, we don't know the function mu t, so we'll just leave it as mu t. Take the differential equation and multiply every term by mu. And we're going to be looking at the left side. The left side looks a bit like this. It looks a bit like the derivative of mu y. The green terms are the same. We have mu dy dt. These are the same. We want the orange terms to be the same as well. We want to have that d mu dt is the same as p mu. We know how to solve this. We can solve this by separating the variables. So move all of the mu terms to the left, here they are. Move all of the t terms to the right, there they are. Because these are separated, we're allowed to integrate. An integral sign on both sides. Integrate, rearrange, and what we find is c multiplied by the exponential function of the integral of p. As before, we can choose any non-zero value of c that we want. I like easy numbers, so I'm going to choose c equal to 1. The integrating factor that we want is not e to the power pt, it's e to the power integral of pt. Okay, so now that we know our integrating factor, our differential equation just becomes derivative of mu y is equal to mu g. We can integrate and rearrange to find the answer. That's the general formula, but in practice it's going to be easier to solve each one using our method. For example, solve the initial value problem, t y prime plus 2y is equal to 4t squared, with the initial condition y of y is equal to 2. Now the first thing to note is our equation doesn't look like the standard equation. This doesn't look exactly like y prime plus p of ty is equal to gt. First thing we need to do is we need to rearrange this equation so it does look of that form. So the first thing to do is to divide everything by t so that we get dy dt plus 2 over ty is equal to 4t. Now we have that pt is 2 over t and g is equal to 4t. We need the integrating factor. The integrating factor is e to the power integral of pt. That's e to the power integral of 2 over t, and that's the same as t squared. So we take our differential equation, and that's the differential equation of the standard form, and we multiply every term by t squared. If we haven't made a mistake here, the left-hand side is just the derivative of t squared y, just the derivative of mu y. Integrate this. T squared y is t to the power 4 plus c, and then divide by t squared. The general solution to the differential equation is y is equal to t squared plus c over t squared. There's one step left. We need to choose the correct value of c. And we can see that to satisfy y of 1 is equal to 2, we want c is equal to 1. So the answer to this problem is t squared plus 1 over t squared. Let me show you a graph of this function. All of these curves are solutions to the differential equation. But for the initial value problem, we were asked to find the solution which satisfied that y of 1 is equal to 2. So in other words, we're asked to find the solution which passes through the point x is equal to 1 and y is equal to 2. So in other words, we're asked to find the solution which passes through this point. And it's the curve which I've shown in red on this graph. I want to make some remarks about this. The solution satisfying the initial condition is a differential function defined on the open interval from 0 to infinity. The solution becomes unbounded and asymptotic to the y-axis as t decreases to 0. If you're unfamiliar with this, t decreases to 0 is the same as saying t tends to 0 from the right. And the reason this occurs is because our function pt, which was 2 over t, has a discontinuity at t equal to 0. There's another function, t squared plus 1 over t squared for negative t. This is not part of the solution to our initial value problem because there's a discontinuity between that function and our solution. The solution to the initial value problem only exists for t between 0 and infinity. As soon as you get to a discontinuity, we stop. We go back to the graph. Now notice that solutions are behaving differently. As t decreases to 0, or as t tends to 0 from the right, these solutions are tending up to infinity. But these solutions are going down to minus infinity. There's a change in behavior here. In particular, solutions for positive c, that's the same as saying y of 1 is strictly greater than 1, are asymptotic to the positive y-axis as t decreases to 0. But solutions with negative c, in other words, y of 1 is less than 1 are asymptotic to the negative y-axis as t decreases to 0. There's an initial value in the middle, in this case y of 1 is equal to 0, where this behavior changes. In mathematics, we have a name for a point or a value where something changes. It's called a critical initial value. In calculus, you studied critical points where the derivative is 0. Same idea here. Behavior changes at a critical initial value. And that's all I want to say about linear equations. Next, I want to talk about separable equations. Let's go back to the general first order ODE. dy dx is equal to a function of x and y. We've just looked at a special type of first order equation called linear equations. Now we're going to look at another special case of first order equations. Equation 7 can always be written in the form m plus n dy dx is equal to 0. One way would be to write m is minus f and n is equal to 1, but there may be many other ways. Sometimes it's possible to do this in such a way that m is a function only of x and n is a function only of y. If we can do this, if we can rearrange our equation so that it looks like mx plus ny dy dx is equal to 0, then the equation is called a separable differential equation. Why is it called separable? Because we could then rearrange further to move all of the x terms to the left of the equal sign and all of the n terms to the right of the equal sign. In other words, it's possible to separate the variables with an equal sign. For example, consider dy dx is equal to x squared over 1 minus y squared. Show that this differential equation is separable and then solve this differential equation. We can rearrange this equation to minus x squared plus 1 minus y squared dy dx is equal to 0. So I have a function only of x plus a function only of y, dy dx is equal to 0. So this differential equation is separable. Now I want to solve this. Now notice that the derivative of minus 1/3 x cubed is minus x squared, and the derivative of y minus 1/3 y cubed is 1 minus y squared. I've got antiderivatives of the green and orange functions. So the differential equation we could write like this. We could write it as derivative of minus 1/3 x cubed plus dy of y minus 1/3 y cubed dy dx is equal to 0. But if you remember your chain rule from mathematics 2, this second term, dy of a function, dy dx, is just the same as d dx of this function. So we just have d dx of some function is equal to 0. Integrate that, we must have that the function is equal to a constant. There's two ways to write this. We could write this as minus 1/3 x cubed plus 1 minus 1/3 y cubed is equal to a constant, or I could multiply by minus 3. There's a mistake here, isn't there? And write this as x cubed minus 3. No, there must be a different mistake. Yes, here's the mistake. This one should be a y. So this should be a y, this should be a y. And then this is correct. X cubed minus 3y plus y cubed is equal to a constant. This same method can be used to solve any separable equation. Let's consider the general equation, mx plus ny, y prime is equal to 0. Let's suppose we know antiderivatives of m and n. Let's suppose we know a function h1 of x and a function h2 of y, such that h1 prime is m and h2 prime is n. Then our differential equation is just dh1 dx plus dh2 dy. dy dx is equal to 0. And by the chain rule, that's the same as dh1 dx plus dh2 dx is equal to 0. And at that point, we could just integrate to write that the solution is h1 plus h2 is equal to c. So, to recap, to solve m plus n y prime is equal to 0, we need to integrate m with respect to x. WRT is a short way of writing with respect to. And we can integrate n with respect to y. And then the solution is then integral of m is equal to minus integral of n plus a constant. But we did basically the same thing in chapter 1. In chapter 1, we separated the variables and then integrated. So we integrated m with respect to x and we integrated n with respect to y. So basically, this is the same method that we used in chapter 1. But inverted commas done correctly, if you want to say that. This is the method I've just shown you is the method that pure mathematicians think you should use. But since they're both basically the same, I say it doesn't matter which method you use. Let's do an example. Solve dy dx is equal to 3x squared plus 4x plus 2 divided by 2y minus 1 with the initial condition y of 0 is minus 1. We can rearrange our differential equation like this. I can move all of the y terms to the left, and I can move all of the x terms to the right. And then I can integrate. Integral of the left side is y squared minus 2y. Integral of the right side is x cubed plus 2x squared plus 2x plus c. The next step is to find c, because we want y0 is equal to minus 1. We're going to replace every x by 0, and we're going to replace every y by minus 1. So we would get 1 plus 2 is equal to 0 plus 0 plus 0 plus c. And then we can see that c must be 3. So the solution to the initial value problem could be written like this. Y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3. we have a solution which includes a function of x and a function of y. A solution like this is called an implicit solution. And sometimes this is the best that we can do. Sometimes at this point we need to stop our answer. But in this example, it's impossible to go further. It's possible to solve y. Now, rearrange this. We have y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3 is equal to 0. This is a quadratic equation. We know how to solve quadratic equations. I'll leave this for you to check. You can check that if we use the standard formula, the y is minus b plus or minus square root of b squared minus 4ac over 2a formula that we all know. What we find is that y is equal to 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. And we just say this is not a typo. This really should be 4 just here. But I'll leave that for you to check. But wait a minute, there's two solutions here. There's a solution with plus and there's a solution with minus. But only one of these is correct. So my question for you is, which of these is correct? Do we want the plus or do we want the minus to satisfy the initial condition y of 0 is equal to minus 1? I'll start a new poll. Try again. The correct answer is that we need to choose the minus. So the solution to the initial value problem is y is equal to 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. A solution like this, a solution where we can write y is equal to a function of x, is called an explicit solution. And I can show you this solution here. The red curve is the solution with minus. There's also a top half, that's the solution with plus, and then all the other blue curves are solutions with different initial values. Now note that our solution is a differentiable function defined on the open interval from -2 to infinity. Another example. Solve dy dx is equal to y cos x over 1 plus 2y squared with the initial condition y of 0 is equal to 1. I'll show you the whole solution written very quickly. This is not a perfect solution. This is not good enough as an exam answer. This is just me writing the bare minimum here. First, take the differential equation and rearrange it so that all of the y terms are on the left and all of the x terms are on the right. If you can do this, then you're allowed to integrate both sides. On the left side, I get natural logarithm of the absolute value of y plus y squared. And on the right side, I get sine x plus c. To satisfy y of 0 is 1, I replace all of the y terms by 1 and all of the x terms by 0. And I get 0 plus 1 is equal to 0 plus c. C must be 1. So an explicit solution to this differential equation is natural logarithm of the absolute value of y plus y squared is equal to sine x plus 1. This equation cannot easily be solved for y, so we're going to leave it as an implicit solution. But we can say some things about the solution. If y is equal to 0, then the left-hand side would be minus infinity, because the natural logarithm of 0 is minus infinity. But the right-hand side is always between 0 and 2. That tells us that we can't have y is equal to 0. We know that y is positive at least one point. We know that the solution needs to be continuous. If it's positive at one point and continuous, and it can't ever be equal to 0, then that means that it must be positive everywhere. It's possible to show that the solution exists on the whole real line, but I'm going to leave this for you to think about. I'm going to move on to the final topic for today's lesson. A short topic on the differences between linear and non-linear equations. If you're following with the textbook, the Boyce de Prima textbook, you'll see I'm not doing most of this section. I'm just picking out a couple of key ideas. The first is an important theorem for linear equations. If we have continuous P and G, continuous at least on an open interval, if the point of the initial condition is in this open interval and y0 can be any number, then the theorem tells us that there exists a unique solution to the initial value problem with this linear equation and this initial condition. And it tells us that the solution exists on this open interval where P and G are continuous. Two important ideas here. First, there always exists a solution, and the solution is always unique. So the theorem tells us that as long as our functions P and G are continuous, then the solution keeps existing. To say this another way, the solution can only stop existing at a discontinuity of either P or G. That's a nice theorem. For nonlinear equations, we have a theorem which is not as nice. Suppose now that f and df dy are continuous on a rectangle. In other words, for t between alpha and beta and y between gamma and delta. Let's suppose that t0 is some point between alpha and beta, and suppose that y0 is some point between gamma and delta. So in other words, look at the picture at the top. Imagine we have this rectangle, t between alpha and beta, y between gamma and delta. We need f and df dy to be continuous on this rectangle, and we need the point t0, y0 to be somewhere inside this rectangle. Then the theorem says there exists some interval inside the interval between alpha and beta where there exists a unique solution to this initial value problem. So to recap, this theorem tells us that a little bit of solution exists. It doesn't tell us if we only have this little bit of solution or if the solution exists further. It's possible that we only have this little bit. It's possible that the solution exists on all of the rectangle. It's possible that the solution exists outside the rectangle as well, but we don't know. All we know from this theorem is that there's a little bit of solution existing and that the solution is unique here. Because the solution is unique, it tells us that two solutions cannot intersect. To understand why, let's suppose instead that two solutions do intersect at a point t0, y0. Then that would mean that this initial value problem would have two solutions. And the theorem says this is not possible. The theorem solution says we can only have one solution. So the key idea to take from this section, an idea which we will be using next week, is solutions to first order ODEs do not intersect. And that's with the proviso that f and df dy are continuous on a rectangle, etc., etc. And that is the end of this week's lesson. Next week, we will finish chapter 2. We'll talk about autonomous equations and population dynamics. We will talk about another special type of first order equations called exact equations. And then finally, we will talk about how we could use substitutions to change difficult equations into easier equations. Do you have any questions? So let me remind you, there's a discussion forum. If you think of a question later, you can ask me on the discussion forum. I'm checking that every day. I'll give you an answer there. Otherwise, you're welcome to leave whenever you wish.